Hello and good morning, CTS231 Section 875 students for the second 8-week term in the fall 2016 semester at Anne Arundel Community College. This is the CCNA 4 course, or the Connecting Networks course, as is the title of the text. And this morning's video tutorial is going to be on Packet Tracer Activity 7.5.1.2, the Skills Integration Challenge for Chapter 7. Now, a quick note on some of the things that Chapter 7 covered that are going to be of paramount importance as you move on, not just only in your Cisco networking career, but just simply in IT in general. As it talked about IPsec, and we talked a lot about VPNs, right, or virtual private networks. Now, let's keep in mind that IPsec is mutually exclusive from the concept of VPNs when we're talking about Gre Tunnels, or we're talking about DMVPN, which is that dynamic multi-point VPN that's now part of the CCNA curriculum, or when you're talking about MPLS Layer 3 VPNs. With all of those, encryption, right, or IPsec is definitely a plus, right? It's definitely an advantage to apply it, right, and to integrate IPsec into your solution. But keep in mind that VPN does not require, again, VPN in the context of Gre Tunnels, multi-point Gre Tunnels, which is what powers DMVPN, or MPLS Layer 3 VPNs. Encryption is not a requirement. It's not mandatory that you have encryption. You'll see in this lab that we do here, where we set up these Gre Tunnels between these routers, we don't do any IPsec, yet everything functions just like it's supposed to. So realistically, if you're running Gre Tunnels, point-to-point Gre Tunnels over the internet, or if you're using DMVPN, which is like a dynamic multi-point Gre Tunnel over the internet, or MPLS L3 VPN, you can overlay IPsec onto it in order to protect those communications. And realistically, there's probably a good chance that you're going to be doing something like that. Maybe not so much in the MPLS L3 VPN scenario when you're using a provider's network. However, it certainly can't hurt, right? So keep that in mind. Just because you see the letters VPN in the name of a Cisco technology, it doesn't immediately imply that it's using encryption. And specifically, again, I want to make sure I'm very clear here that we're talking about just a regular VPN with Gre Tunnels, or DMVPN, or MPLS Layer 3 VPNs. Now, when you look at Flex VPN or Git VPN, right, which are other Cisco VPN technologies, that analogy doesn't 100% hold up. All right, so we've got quite a bit here in this Skills Integration Challenge. This is a fantastic activity, really builds on everything from Chapter 7. And let's go ahead and dive in. Now, one of the first challenges that learners run into is this statement right here. You only have console access to router 1 and Telnet access to the HQ router. Well, okay, great. Well, what happens if I click on router 1? It tells me that the configuration is locked. Now, this is how we've been accessing the console on these routers throughout the course. As you would click on the router, it would come up and you would say CLI, and it puts me on the command line interface right here, and I am using the console port to make that happen. Now, when I click on router 1, it doesn't let me do that, and so this is like one of these little Cisco tricks or diversions that you get into here, is that learners are clicking on router 1, they're seeing the configuration is locked, and they're like, well, what's wrong? Something's wrong with the packet tracer activity. Well, yes and no. What's wrong is that they're making this exceedingly difficult by not telling you that the console connection, you need to come down here to the lightning bolts, right, or the connections. It represents a serial link there. And then if you hover over this blue cable, which is the same color as the Cisco rollover cables that you get with the equipment that you order, you can see down here in the center it says console. So if I were to click on that and come to the PC, we'll do it from PC 1, and I click on the RS-232 port, that's the port to which I would connect my console cable, and then I would connect it to the console port. And so this is actually what they're trying to say here, is that you only have console access to router 1, but they don't tell you that you actually need to put the console cable in there. So this can be a little frustrating at times. So anyway, that is how you get the console access. So now the question becomes, okay, well, I can click on router 1, right? No. Remember, the console access is going to be from the terminal PC1. Now, what I've never tried to do, I've never tried to connect it from PC2, and that wouldn't make sense because, you know, you'd have to drag it way over here. Not to say that it wouldn't work. Excuse me. So let's click on PC1 here. We're going to drag PC1 to the side. Let's shrink the window a little bit, but then let's make it a little wider. Now, when I come to the desktop, you can see I've got all kinds of different applications that I can take a look at here. And remember, from the PC, it's all about the terminal applications. That's how I'm connecting to the console line. Now, the print here is going to be small, unfortunately. But I will verbally let you know each of the commands that I'm running. So here we are. We're on router 1. Now, another thing that that can become frustrating is, remember it says up here we have Telnet access to the HQ router. So if I type in Telnet 10.0.0.1 and hit enter, excuse me, you'll notice that it's just simply going to time out, right? And the host is not responding. And this is because we need to do all of the, well, not all of the configuration steps, at least the frame relay configuration steps in the router 1 setup before we're going to have connectivity through this frame relay cloud in the middle here up to the HQ router. So let's go ahead and take care of router 1 first. So let's go from user exec mode to privilege exec with the enable command. And then into global config. So we're doing full mesh frame relay. And we can tell that because we don't have point-to-point sub interfaces set up here in our environment. We're actually using the entire physical interface without carving it up into sub interfaces. And so that's what full mesh means. Full mesh also means that everybody in my frame relay cloud, we are all on the same IP subnet. Now, this is also sometimes a point of confusion for learners where you have those zeros in the second and third octet, and we say it's a /29. So with a /29, how many host bits do we have left? Let's get our block size first, because we want to figure out what the usable IPs are, what our network ID is, which is actually kind of self-evident here. That's going to be the network ID. And then we want to know the broadcast address. Well, if we have 29 network bits, that means we have 3 host bits left. So I raise it as the, I believe it's exponent is the mathematical term here. So 2 to the 3 is 8. Remember, 2 raised to the power of the number of remaining host bits after I do my borrowing, right? I'm taking away host bits and turning them into network bits. I've got 3 host bits left. So my block size is 8. Well, this is my network ID. So from here, it's pretty much all of the subnetting is pretty much done. If you can figure out the number of host bits left, which is very simple, because you look at your CIDR notation or you look at your dotted decimal notation for the subnet mask, you can determine the number of host bits that are left. That gives me my block size. So again, we're doing a little review here of subnetting. So if my block size is 8, my first network ID is .0, then it's going to be .8, .16, I'll just write over this here, .24, .32, .40, .48, and so forth and so on, and we just simply continue to go up in 8s. Now, each of these is its own subnet, right? So now this is going to easily, and actually I should probably put a line through here, this will make it so easy for us to take a look at this and say, oh, well, if .8 is the first address, and this is the network, I'll just say NID, this is the network ID for subnet number 2, and this is subnet 3, and subnet 4, and so forth and so on, right? ... So what's the last IP address? What is the broadcast address going to be here in subnet 1? Exactly. It's going to be the last address before the network ID of the next network. So it would be .7. And then and I'll put bcast down here. Pretty shabby B. Bcast down here. This is our broadcast address. So here it would be 15. What would it be here? Exactly 23. What would it be here? Exactly 31. It's basically just one less than the network ID of the next network, right? So from this, in the network that we're interested in, we see our broadcast address, .7. We have our network ID. So now we know that our usables are going to be from .1, and we'll say ... down to .6. So with a /29, we have 6 usable IPs, and ours just happen to be 10.0.0.1 to 10.0.0.6, and then inclusive, right? So .2, .3, .4, .5, and .6. So let's go ahead and clear our screen here. So if we come back over here, let's take a look and see how are we configured right now. So how about a do show IP interface brief, and we can see that we are up down right now on serial 10003. So let's say do show run. Let's see what serial 00 looks like. So as you can see, we're set up with the right IP address, the right subnet mask. This is our frame relay full mesh link, but the encapsulation is PPP. So we know that's where we're going to start. So let's jump into interface serial 000, and we're going to configure frame relay encapsulation. And if you look, there's really only 3 choices of encapsulation here, right? Frame relay HDLC, which is the Cisco proprietary, so it's really CHDLC, because Cisco took the standard HDLC and then added in their secret sauce. And so that's the Cisco HDLC. It's also the default encapsulation method for Cisco serial interfaces. And then we've got PPP, the point-to-point protocol, which is what it's currently configured for. But we're going to say encap frame relay, right? And you can see we picked up 2 points there. So we're changing the encapsulation to frame relay. Configure a map to each of the other routers using the broadcast keyword. So what that means is we're going to be configuring static frame relay maps. Well, if I'm using static maps, and this is something that when we were talking about frame relay in the chapter, and I think it was chapter 4? Chapter 4 we did frame relay. When we looked at doing a static map, that means that we don't need inverse ARP turned on. Now remember, when we talk about inverse ARP, and this is what we're basically creating a static mapping of. So let's take a step back. Remember ARP, right? Address Resolution Protocol. This means I know my layer 3 address, right? So if I were to say ping 10.0.0.1, I know the layer 3 information. What I don't know is the layer 2 information. In other words, what is the MAC address, right? What's going to be that next hop or that layer 2 information that I need to know in order to get to the destination? With inverse ARP, as the name implies, I'll just put INV ARP. With inverse ARP, as the name implies, I know my layer 2 information, and in a frame relay context, what are we talking about? The DELC, right? That data link connection identifier. And we have a table right over here of all of the DELC values that we're interested in. So I know the DELC information, but I don't know is the next hop layer 3 information, or the IP address of the destination, right? So I know the local layer 2 DELC information. Remember, that's locally significant. It's a locally significant value that I create, but I need to map it to this layer 3 destination IP so that I know out which DELC, which data link connection identifier, I need to go to reach this layer 3 destination. And inverse ARP does this auto-magically for you. But the requirement here is to configure a map, right? So, and what that basically translates to is a static, right? Because if we're manually creating it, if we're manually configuring it, it is a static frame relay map, at which point we don't need inverse ARP, because we're basically hard coding the information that we would typically receive from inverse ARP. So let's go ahead and clear our palette here. And let's come down onto serial. We're still in serial 000. So we're going to create a static map. But first we're going to say no frame relay inverse ARP, because we don't need inverse ARP on. We're not going to depend upon it because we're creating the mapping statements manually. So frame relay map IP, and you can see it says protocol specific address. Well, it's the destination IP address, right, that we're going to map to the layer 3 DELC value so that we can get to that other router across the frame relay cloud. So if we do, we're on router 1, so let's do HQ, and HQ is 10.0.0.1, and then my DELC value is going to be what? So if we refer to the table here, you can see that router 1, the DELC value for HQ, which is, and this is locally defined, is going to be 301. So I would say, let's come back down here to the command line and say, oh, sorry, and I forgot the broadcast keyword. And you can see, so it says it's already in map. So let's say do show run. Let's see if it's got the frame relay. It does. So we're going to pull that out. That was my mistake there. I apologize. We'll say Control A. So no frame relay map IP, and then let's pull our command back, and where are we at? Frame relay map and broadcast. Now, remember, we need that broadcast keyword in there if we have any hopes of if I remember correctly, this is running EIGRP, I believe. So if we want EIGRP to function, we have to put that broadcast keyword in there because we're telling frame relay that this static mapping that we've just created needs to support broadcast. And by definition, if it supports broadcast, that means it will also support, I was going to say unicast. It already supports unicast. It would support multicast, which is what we need, right? And if it's EIGRP, we're looking at that 224.0.0.10. Or if we were doing IPv6, we would be looking at FF02::A for EIGRP's multicast address. So now let's go ahead and add in the statement for router number 2. So the frame relay static mapping statement for router number 2 would simply be frame relay map IP 10.0.0.2, 302 is the DELC value, and broadcast. Again, we need to tell it to support multicasts, right? So we have to use a broadcast keyword because, again, by definition, if I say broadcast, and you'll see there is no, if I come back here, there is no multicast keyword. So you say broadcast, and that basically implies, by definition, multicast. All right, so that takes care of the frame relay static mapping statements. And again, that's why we do not need inverse ARP at our disposal here. So if I were to say, well, actually, let's do the LMI type first. So the LMI type is ANSI. So again, I just simply say, not farm, but frame relay LMI type. And if I look at the LMI types, we've got ANSI, which is vendor agnostic. So I could be doing this between a Cisco router and an HP router or a Juniper router. Or I could say Cisco, which is the Cisco proprietary, but we are going to be using ANSI, right? So I say frame relay LMI type ANSI. I was going to say we should see some connectivity here. You can see the serial interface comes up, and then we get the neighbor message from EIGRP up. So if I were to say do show IP EIGRP neighbors, I should have 2 neighbors. I do. The HQ router and router 2 do show IP route EIGRP. And so I'm learning EIGRP information. And so this is what I was referring to when I said that we would have to get the frame relay connectivity working first. If I were to go do ping 10.0.0.1 now, you can see now we have connectivity. Whereas before, when I tried to Telnet, there was no connectivity there. We had to get the frame relay connectivity working and established before we dive in here to connect into the HQ router. All right, so the next step says configure GRE tunnels to the other routers. So we're going to go ahead and do this now, because what you'll see is once we Telnet, and to get to that HQ router, we go from here. We go from router 1. So we don't want to have to go over to the HQ router and then exit and come back out and then telnet back over. So we're going to do everything here on router 1 first. So it says configure GRE tunnels to the other routers. Now, what I'm doing here is I'm just simply creating an overlay. I'm going to introduce you to two new terms here in this tutorial: overlay and underlay. And so GRE tunnels are considered an overlay technology. In other words, I'm going to layer or overlay a GRE tunnel put on top of the underlay transport technology. And so what exactly does that mean? Well, what we're talking about here is the underlay is my frame relay, right? Because frame relay is providing me the layer 3 transport between all three of these routers. So that's the underlay technology that is going to allow me to apply GRE tunnels that I simply lay on top of the frame relay underlay connectivity, right? So again, overlay and underlay. So GRE is an overlay technology because we are layering it or putting it on top of the existing layer 3 transport, right? Excuse me, or the existing transport technology, in this case frame relay, which is the underlay. And again, we can't have the overlay, and think of it like this logically. I'm not going to be able to do an overlay if I don't have underlay reachability, right? If I don't have transport between these routers via frame relay, my GRE tunnels, right, just like the Telnet didn't work. The GRE tunnels at that point are pretty much useless, because if I don't have reachability up here, from router 1 up to the HQ router and over to router 2, the tunnels aren't going to work, right? So we have to have that underlay technology. So let me get rid of that spaghetti mess there. Okay, so we're on router 1. We're consoled into router 1, I should say. So now let's go ahead and let's configure these GRE tunnels. So I simply, just like you would create, or you would go into configure, I should say, not create, but just like you configure any other physical interface on the router, we're going to configure a logical interface, but it's done in the same fashion in terms of, I say interface tunnel 0. Like I'm pretending I'm going into physical interface tunnel 0, but the tunnel is nothing more than a virtual interface, right? So it's a software interface. It's not a hardware interface. There is no interface on router 1, no physical interface into which I'm plugging a cable and that interface is labeled tunnel 0. No, remember, this is an overlay. So I'm going to put this virtual software interface, right? Think of it like a virtual machine. Okay, it's a virtual machine that runs on top of physical hardware. And this is the same way. This GRE tunnel interface is a virtual interface that's going to run on top of the physical serial 000 interface. But it's mutually exclusive, right? So it's its own little virtual machine. Think of it like a little virtual machine interface that runs on serial 000. And I could create tunnel 0, tunnel 1, tunnel 2, excuse me, and create as many virtual interfaces as I needed, right? So now that we're in there, we need to put the IP address. So let's say IP address 192.168 and tunnel 0 on router 1 is .1.6, and these are all /30s. So 255.255.252 is my subnet mask. Now, I need to tell it, right? It's a virtual interface. So while it does know its IP address, it doesn't know the source interface, the source physical interface on this router over which I want to lay it or place it, right? The overlay. So I just simply need to tell it. So we'll say tunnel source is serial 000, and now it knows which interface it's supposed to use to egress to get to the other side. In other words, our destination. Now remember, the source is going to be an interface in this scenario, and the destination is going to be obviously an IP address that is across our frame relay cloud. So I say tunnel destination 10.0.0.1 1. And as you can see, that interface just changed to up. So, and I think we need to do the tunnels on HQ, so we're probably not going to have reachability there. So there you go. So do show IP interface brief. And you can see our tunnel 0 interface. It shows up just like all of the physical interfaces do. We get the same information, but what we see is, and what we know, I should say, what we know is that this is a virtual overlay VPN, virtual private network. Okay? And remember, make sure that in the context of our discussion, when we're talking about DMVPN, or we're talking about MPLS Layer 3 VPN, or whether you're talking about this VPN here, that virtual private network does not intrinsically mean that encryption has to be put on there and that encryption is running. There is no encryption here. No IPsec, I should say. Probably a better way to say that. Encryption is just going to give us our confidentiality, right? It's going to encrypt the data, but IPsec is sort of a larger umbrella of security protocols that end up getting used. So again, VPN doesn't necessarily imply that encryption is being used or that IPsec is being used. All right, so let's get our the second tunnel interface. So interface tunnel 1, right? Let's get our IP address on here, just like we would a normal physical interface, 192.168.1.9, and it's a /30. And again, since it's a virtual interface, I need to tell it what the source interface is, and that's again going to be serial 000, and what the destination is. And so the tunnel destination is going to be 10.0.0.2 over to router 2. So now that's it. On router 1, I've created my tunnel interfaces, do show IP interface brief, and I have tunnel 1 and tunnel 2. So can I ping to the other side? Let's say do ping 10.0, I'm sorry, we're going to ping the tunnel IP addresses, 192.168.1.10 on tunnel 2. And take a look at that. There you go. So I now have this blue line that you see here. What I have is I've got a virtual private network between these two routers, and it appears as a point-to-point interface. And that's a key point, no pun intended. That's a key concept, I'll say, to avoid the pun. It's a key concept that needs to be understood, is that that tunnel right here between the tunnel 1 interfaces on router 1 and router 2, router 1 and router 2 now believe that they have a point-to-point connection. They don't, over this tunnel interface, the tunnel interfaces don't realize that they actually come up into this frame relay cloud. And this cloud, let's say you could have 10 frame relay switches that you have to go across. But router 1 and router 2 see this interface as a single hop because they view it as a point-to-point interface. And again, you can do point-to-point GRE tunnels over the internet. And think about that. If you had an office in New York, and there's our New York router, and an office, we'll put it way over here in California, and actually, let me clear that, because that's backwards. You had to say it's out here in California, just from left to right, over to the East Coast, from the left, I was going to say the left coast, the West Coast to the East Coast, right? You could have all kinds of different routers that you're, and you will, that you're going to be going through to get from your office in California over the internet, right? We're going to say this is that big bad internet cloud, right? This is the internet. You're going to be going through all kinds of different routers before you actually get to the New York office. So when you do that GRE tunnel across the internet, and we'll stick with the blue, right? And I create this virtual private network over the internet, the New York router and the California router, they see, we'll say tunnel 1, they see the virtual interface. That's all they see, right? This is what they see. And so they believe that, hey, we have a point-to-point connection between us, even though technically it's not. It's going, in our case here, there's a hop there, a hop here, a hop here, a hop here, a hop there, and then ultimately the final hop. So that's what GRE is providing. It's giving the routers the impression, right, that they have a point-to-point interface, even though it's going across a transit topology that could have 5, 10, 15, 20, 50 routers in between, right? And that's the beauty of the GRE tunnels, is that you can encapsulate literally anything inside of GRE. So both of the tunnel interfaces are up. We've got connectivity on router 1. So things on router 1 are just about, let me make sure here. Yeah, I believe we are complete on router 1. So let's go ahead and say end. We're going to say write mem, save our configuration, and now let's telnet over to HQ. So that's going to be 10.0.0.1. All right, so the username is admin, and the password is admin pass. And so now we're into the HQ router. Let's get into global config. We'll say do show IP interface brief. And none of the tunnels are configured here on the HQ router. So the first thing, we'll actually take these in turn here. So configure HQ to use PPP with CHAP. So the point-to-point protocol with the challenge handshake authentication protocol. So let's go ahead and say do show run. Let's see what our encapsulation is on the serial 001 interface. And remember, we're looking at this link to the ISP here. So we're configuring the challenge handshake authentication. But remember that typically it's only the provider that needs to issue the challenge. And then the customer, right, will respond back to the provider challenge. And logically, if you think about it, that makes sense, because typically it's not the customer who's trying to challenge the provider. Now, you can set it up like that. There's absolutely nothing wrong with having mutual, right, or two-way authentication. It's just that keep in mind that it's not required, and historically it was the ISP that would issue the challenge handshake authentication and not the customer. And so let's come down here. Whoops, almost dropped my pin there. So we'll come down here to the HQ router. Let's get into interface serial 001. And the first thing we want to say is encap PPP. We want to make sure we change the encapsulation to the point-to-point protocol, and then we're simply going to say PPP authentication CHAP. Now, if I do the question mark here, we're going to see that PAP pops up. And you might be asking yourself, well, if I already chose CHAP, why does it show PAP? Remember, from chapter 3, I believe it was, with the point-to-point connectivity, that you can have multiple authentication means, right, or options implemented when you set PPP authentication up. So if I were to say PPP authentication CHAP PAP, I'm saying first try to authenticate with CHAP. If that doesn't work, then try to authenticate with PAP. But we don't need that here. I just wanted to make sure we kind of reviewed that. So I'm going to say PPP authentication CHAP. I was going to say PAP there. So PPP authentication CHAP. All right. So excuse me. So now that we've got that set up, we're going to need the username and password, which it provides us over here to the right. So let's exit out to global config, where we're going to say username is ISP, and then the password. And remember, I can't say secret there. There was that one lab, I think it was 3148 or something like that, where it had us use secret. Keep in mind, you can't do that. It will not work. The authentication will not function properly if I were to say username ISP secret, because I'm creating an MD5 hash of the password. And so I can't hash a hash, right? You can't do that. So we have to leave it as just password and say, is that right? Cisco. So username ISP, password is Cisco. So now let's say do show IP interface brief. We should see serial 001 is now up. So let's try to ping. So do ping 209.165, whoops, .165.201.2. Well, actually, we are 2. So it's a /30. My guess is they are going to be .1, and there we go. We've got connectivity, right? So the PPP portion is done. So now we go back to doing some tunnels, right? So let's go ahead, interface tunnel 0, and this is the tunnel that goes to router 2. So the IP address for HQ's tunnel 0 is 192.168.1.1, and this is going to be a /30, 255, 255, 255, 252. And again, I need to tell this virtual tunnel interface what physical interface it's going to be using, serial 000, and then I need to tell it the other end of the tunnel, the destination end. Where does the tunnel end, right? Like you go into the Holland Tunnel in New York, And the source is wherever you enter, and then the destination, right? Or how do I come out? And the destination is you come out on the Jersey side, right? Or theoretically, you're coming out on the Jersey side. So we'll say tunnel destination, and we'll put this IP address in here of 10.0.0.2. Right, remember we put the underlay. We don't put the 192.168 because that's the tunnel IP. We have to give it the IP address over which layer 3 reachability has already been established. That's the underlay. And sometimes you'll hear it referred to as the physical interface IP address on the other side. And I can't say tunnel destination serial 000 because that makes no sense, because then I still have no idea the IP address to which I'm going to get to that interface. All right, so then interface tunnel 1, IP address is going to be for HQ 192.168.1.5, and the tunnel is a /30, and then we've got tunnel source, TUNNEL. Tunnel source is serial 000, and my destination is 10.0.0.3 for router 1. And let me make sure that I've got this correct. Yeah. So as 10.0.0.3 for router 1. Okay. So that takes care of our GRE tunnels, right? Our little virtual private networks that, remember, they're VPNs, but they are not encrypting anything, right? If you're interested in that, definitely take a look at the CCNA security documentation or texts, and they are fantastic, and they go a little deeper into IPsec and how to implement these tunnels and protect the tunnel, right, by encapsulating it with IPsec. Okay, so now we're on to NAT, and this should be pretty straightforward here. So configure NAT to share the public IP address configured on interface serial 001 with the entire Class A private range. Now, here is where this could be a little tricky. Is that we're not using a pool. We're using the interface. So let's get the access list in here. And when it says that entire Class A range, it's talking about our 10 dot range. So the access list, let me exit out here. Access list 1, permit 10.0.0.0, 255.255.255. So that's how you would create an access list that is going to match or permit the entire 10 dot Class A RFC 1918 addressing space to be able to use NAT, which is what we want. And those PCs that you can't see right now that are behind this window, those are the PCs we're going to be using to test. All right, so we've got our access list in here. So now we need to go ahead and associate the access list with the single interface. But remember, we're talking about what could be, and if my math is serving me right, it's like 16.7 million host addresses, I believe, is what we could have in here. The number of usable host addresses with a /8, right, or a 10.00 could be 16 million, 16.7 million, right? Now, we've subnetted some things here, so we're obviously losing addressing, but it's a lot of addresses. So we're not going to do a dynamic NAT pool. We're going to have to do what? Not static NAT, not dynamic NAT, but we're looking at doing NAT overload or PAT, port address translation. Again, leveraging that single interface IP address on serial 001, which is our 209.165.201.2, but we're now going to be using UDP and TCP port numbers to differentiate all of the individual connections that are going outbound, and then on the return, we can translate those back and make sure they get to the right originator. So we've got our access list, so now we're going to say IPNAT source, and actually let me get IPNAT inside. I always get inside and source mixed up. IPNAT inside source. Now, I say list, right, because we've got this access control list, this ACL, which is ACL 1, standard ACL. Now, typically with dynamic NAT, this is where I would say pool. And even with NAT overload, I could create a pool. But what am I doing here? I'm associating the ACL to a specific interface. And all this means is this is avoiding me having to create a pool with a single address and then overloading the pool at the end. Because if I know I'm only using the one address, it doesn't make sense for me to say, or to create a pool that would have 209.165, 201.2, and then to end it at 209.165.201.2. That doesn't make any sense, right? Now, you can do that, but again, we're using the interface, and we're using that interface IP, so we can simply say interface, and then we put down serial 000. Now, this is critical. If I hit enter here, we're in all kinds of trouble. I have to have the overload keyword in here to allow multiple clients, right, in our case 2, to get out using PAT. That overload keyword says we are using port address translation. We are overloading NAT. And so I hit overload and I hit enter. Now all that's left is for me to get into serial 000 and say that is my IPNAT outside interface, and then come into serial 000, or wait a second, I did that backwards, hold on, 001. So let's go to serial 0, and let's actually pull this off. So no IPNAT outside. So this is IPNAT inside. The serial 00, excuse me, the serial 000 interface is my IPNAT inside. Let me make sure we've got this correct. So there's the IPNAT inside, and then interface serial 001 is my IPNAT outside, right? So I've got my outside interface and my inside interface both defined here in terms of NAT. And so it looks like we are short on 3 points. Let me take a look here. That should have done it, unless me putting the IPNAT. Let's go back into serial 000, interface serial 000. And you can use extra zeros, it's okay. So we say interface serial 000. I'm going to say no IPNAT inside. And then do show run. Let's make sure it pulled it off there. And it did. And let's try to add that back in, because I believe this is what we're missing, IPNAT inside on the serial 000 interface. And that should be the 3 points that we are lacking here, and it does not appear to be the case. Let me take a quick look here. Let's go ahead and check our results, and let's make sure. Inside source list. Yeah, it's definitely something to do with the NAT configuration. So inside source list, that should have... Oh, did I put the serial 000 interface, didn't I? All right. Fortuitous failure here. So let's come back to the HQ router, and I am guessing that what I said, do show run include NAT. Before I even hit enter, I will almost guarantee you that for the interface, I said serial 000. Instead of serial 001. So got stuck on the serial 000 interface. Let's exit out. We're going to say no IPNAT inside source list 1 interface serial 000 overload. Whoops. Overload. So we're going to take that off, and we're going to get the right interface in here. So IPNAT inside source list 1. Source list 1 interface. Let's get the right interface in there. Serial 001 overload, because that is my true outside interface. And so that's going to bring us to 100 out of 100. Okay, well, that is going to wrap up Packet Tracer Activity 7.5.1.2. Again, easing us into how to create GRE tunnels that create a virtual private network that goes over, right? It's an overlay technology, GRE. We overlay that on top of the underlay transport network, which in this case is frame relay. We did some NAT. We made sure we got the right interface in there that we tied to our source ACL on the inside. And that is it. So finally, I guess we can quickly check for connectivity here. So if I drop out of that and get into the command prompt, I should be able to say ping 209.165.200.226. And we're probably going to have to ARP out here using the address resolution protocol to get my default gateway, and then boom, everything works great. I come to the PC. I go to the desktop, we come to the command line interface, and I say ping 209.165.200.226, and take a look at that. All right, we've got connectivity all the way around. All right, thanks so much for watching. I hope that this has clarified the concepts and the application of those concepts from Chapter 7, specifically the Gre Tunnels, and then taking some other chapter work, Chapter 3 with our PPP, and Chapter 4 with Frame Relay. And keep in mind that Frame Relay is going to be sunsetting. As I said in the opening, Frame Relay as sort of the non-broadcast multi-access technology is sunsetting and is going to be replaced by DMVPN, which we also talk about, or I should say, which you also see in the course curriculum online. All right, thanks for watching, guys. Enjoy the rest of your weekend.